Lesson 923, Confidence Intervals for Paired Samples. In previous lessons in this module, we used sample data to make inferences about the mean of a population. In this lesson, we will make inferences about the mean difference between two measurements. We will learn how to construct interval estimates on paired data. Read the descriptions of the two samples below. Measuring blood pressure. Doctors evaluate young children for possible cardiovascular abnormalities, problems with the heart. These abnormalities, or defects, can lead to heart illnesses or serious health problems. To check a young child's heart, doctors need to evaluate his or her blood pressure. Blood pressure tells doctors how well the heart is pumping blood into the body. Continuous blood pressure monitoring gives the best results and is desirable. Historically, doctors monitored blood pressure by inserting a catheter into a patient's artery, a blood vessel that carries blood from the heart. This type of catheter is a thin tube with a blood pressure sensing mechanism. The catheter method can be dangerous. It is very invasive. That is, surgery has to be done to insert the catheter into the patient's body. Invasive methods have a high risk of infection and internal bleeding. In response to this concern, a new non-invasive method called FINAPRESS, which stands for finger arterial pressure, is used. No surgery is needed for this method. With this method, doctors attach a small clamp called a cuff to a middle finger. The cuff is connected with a wire to a monitoring device. Researchers want to know whether the results for the two methods are the same on average. In order to study this, a researcher measured the blood pressure of 15 young children. She decided to compare the catheter method and the FINAPRESS method. She used the two methods at the same time. The FINAPRESS cuffs were applied to the child's right middle finger. Catheters were inserted into the child's lower arm. The diastolic blood pressure results are shown in the table below. So this table has two columns, one for the FINAPRESS method and one for the catheter method. Here's another sample example. Woodpecker bill lengths. Woodpeckers are birds that drill holes in trees using their beaks. A woodpecker's beak is called a bill. Biologists who study birds have noticed that male and female downy woodpeckers drill holes in different areas of trees. The biologists are curious about this difference in woodpecker behavior. They wonder if it is caused by differences in the physical characteristics of male and female woodpeckers. One theory is that birds with longer bills can drill deeper into a tree. Perhaps there is a difference in the length of male and female downy woodpecker bills that explains why the birds choose to drill in different locations. Imagine that researchers wanted to study downy woodpecker bill lengths. The researchers caught 12 male and 12 female randomly selected downy woodpeckers. Before the researchers released the birds again, they measured the length of each bird's bill. The bill measurements are shown in the table below. The researchers would like to know whether their data provides evidence that male and female downy woodpeckers differ in mean bill size. So here's another table with two columns, one for male bill lengths and one for female bill lengths. Summary of all of those examples we just looked at. In both the blood pressure and woodpecker examples, two sets of data were collected. In the blood pressure study, blood pressure was measured using 1, the FINAPRESS method, and 2, the catheter method. These two measurements were taken for each child and paired together. In the woodpecker study, researchers measured 1, the length of male woodpecker bills, and 2, the length of female woodpecker bills. In one situation, the two data sets are directly related. This means the data are related in a pair, a value from one data set and its corresponding value from another data set, and the data are measured from a single individual. So two data sets are directly related. They are related in a pair. They are measured from a single individual. We call such data paired. Paired samples are also called dependent samples. In the other situation, the two data sets were not directly related. In fact, the values of one set have no effect on the values of the other set. We call such data independent. So independent data two sets that were not directly related. Number 1, which situation includes independent samples? Explain why you think this context's data is independent. So we have two data sets. The first one, we had blood pressure readings and we had Finepress and catheter methods. And remember that for each child, they had Finepress cuffs and a catheter, whereas the other data set was male and female birds, and then measuring their bill lengths. So which situation includes independent samples? This would be the birds, and it's quite simply males are independent of females, and vice versa. Male and female birds are independent of each other. So then number 2, which context includes paired data samples? This would be the blood pressure readings. And the reason why is that in that table, each row actually represents two different readings by two different methods, but they're on the same child. So the first row, you could say, is child 1, and then the second row is child 2. So you have two different data values, but that's because there are two different methods for measuring blood pressure. So we can say, for answer for number 2, the paired data samples is blood pressure, and the explanation is each child had two readings. So summarizing what we just looked at, two samples are independent if the selection of elements in the first sample does not affect the selection of elements in the second sample. Two samples are paired if each data value in the first sample has a corresponding data value in the second sample, such that the two values were measured on the same object or individual. Paired data consists of two measurements for each of a single set of objects. Investigating differences in paired data. Next, we investigate whether the catheter method and Finepress method generate different measurements of blood pressure on average. Number 3, imagine that there was no difference between the two measurement techniques. That is, the two techniques should result in roughly the same values for the patient. If this is the case, what would you expect the difference in the two values to be, or to be close to, for a given child? So hint, difference is equal to Finepress value minus catheter value. Also off to the right where it says language tip, words like roughly, approximately, or about are used to show that the values are not exact but are around a particular value. These words are often used in statistics because we cannot make larger claims than the data allows us to make. So for number 3, if we're thinking that we are looking at the difference between the two values and they're telling us that there was no difference, maybe just think that for number 3, if we're imagining that there was no difference, the number that stands for no difference would be 0. So if this is the case, what would you expect the difference in the two values to be? We would expect them to be close to 0. A certain amount of variability in a child's blood pressure from the time of one measurement to another is natural. Therefore, we wouldn't expect all differences to be exactly 0. Because of this, we will examine the average of the differences. We will use the mean of the sample differences to draw conclusions about the population mean of differences. Number 4, complete the table below. Calculate the difference x minus y for each data pair. So what they have done is they have assigned the letter x to stand for the Finepress method. So below the word Finepress, we have all of the numbers that went for the blood pressure readings for that method. And they're just labeling that data set as the x values. And then the catheter method, we have numbers below the word catheter. Those are all of the y values. And notice off to the left, the first column says child number. And here you can see 1 through 15, the 15 different children, and how they have 2 different measurements for the 2 different methods. So all they want is just take the number for the Finipress method and subtract the number for the catheter method, and that gives you the difference that they call x minus y. So for child 1, that would be 23 minus 31. And you can just use a calculator for this. That would give you negative 8. For child number 2, that would be 30 minus 38. And that would also be negative 8. And for child 3, that would be 30 minus 30, which is just 0. And then for child number 4, 45 minus 43, and that would be positive 2. So notice for some of these you're going to get negative differences, for some you're going to get positive, and for others you may just get a difference of 0. So then for the rest of these children, child 5, that would have a difference of 16, and you can check these on your own. Child 6 would have a difference of 0. Child 7 would have a difference of 2. Child 8 would have a difference of negative 16. Child 9 would have a difference of negative 8. Child 10 would have a difference of 1. Child 11 would have a difference of negative 4. Child 12 would have a difference of negative 20. Child 13 would have a difference of negative 2. Child 14 would have a difference of 4. And finally, child 15 would have a difference of negative 3. So number 5 says determine the mean of the sample differences, and number 6 says determine the sample standard deviation of the sample differences. That means I am treating this new column that we just got, the differences, as a single list. Those are just a list of differences. So put all of those numbers into one list. So put these answers And when I say put that into one list, this is where, again, we want to use our TI-83 or 84. Press the Stat button. Then on the Edit screen, click Edit, choose a list, delete anything that's there, and just enter these 15 differences into one list. And then after you've done that, you can use Stat, and then Calculate, and then one variable stats to get the mean for that list and the standard deviation for that list. And what you should get for the mean would be negative 2.933. And then for the sample standard deviation of all of those differences, you should get 8.573. So you can see that throughout this whole module, we've been using one variable stats. So we definitely want to become very familiar with that. Number 7, think about the context of the children's blood pressure measurements. Remember, we are trying to see if the new Finipress method produces different measurements on average than the more common catheter method. Also recall that the population mean of all differences is the average of all differences. If you found that the population mean of all differences was negative, what do you think this would mean in context? In other words, how would you interpret a negative population mean of all differences in this situation? What we want to think of is this idea for subtraction that we were doing was taking the Finipress method minus the catheter method. And under that subtraction, if we were getting negatives, which number would have to be larger on average? If you get a negative from a subtraction, it means that the second number has to be larger on average. So this means that the catheter method is recording higher blood pressure. if we're getting negative averages. So catheter method is recording higher blood pressure. And since we're talking about an average, it is recording these higher blood pressures on average. You could also say the Finepress method is recording lower blood pressure readings on average. So number 8, imagine that you found that the population mean of all differences was positive. In the context of the children's blood pressure measurements, what would this mean? So since positive is the opposite of negative, this answer is just the opposite of what we wrote for number 7. So this would say that the Finepress method is recording higher blood pressure, again, on average. Number 9, in the context of the children's blood pressure measurements, what would it mean if the population mean of all differences was 0? So this is essentially saying that the two methods are giving the same reading, but again, on average. The two methods are giving the same reading, the same blood pressure reading on average. By the way, the secret word for this lesson is pressure. So now we move on to concluding this whole lesson, estimating the population mean of paired differences using a confidence interval. We now have a basic understanding of samples of paired differences. In previous lessons, we learned about confidence intervals. Given a sample of paired differences, we can apply confidence interval techniques to create an interval estimate for the population mean of paired differences. The sampling distribution of means of sample differences. From our past work with single populations, we know that the test statistic for a sample mean, t equal to x bar minus mu divided by the fraction s over the square root of n, follows a t distribution with n minus 1 degrees of freedom. This test statistic uses a sample standard deviation rather than a population standard deviation. Assume that the population of paired differences is approximately normal. In this case, the test statistic for a mean of sample differences also follows a t distribution. Constructing confidence intervals for the population mean of paired differences is similar to constructing confidence intervals for a population mean, meaning what we are going to do for this lesson is actually the same as what we were doing for a previous lesson. Below are formulas and instructions for constructing confidence intervals for the population mean of paired differences. So first, the mean of the sample differences, x bar, is the point estimate for the population mean of the paired differences. The margin of error for a confidence interval for the population mean of paired differences is the same formula we saw before. Capital E equal t sub c times the fraction s over the square root of n, where t sub c is the critical value based on the confidence level and degrees of freedom, s is the sample standard deviation of sample differences, and n is the number of paired differences in the sample. Using the point estimate and margin of error, the confidence interval for the population mean of paired differences is x bar plus or minus e, or as we've seen before in the interval notation, x bar minus e, x bar plus e. And you can also see that at the bottom here where they've written out the formula for e. So the following questions refer again to the differences between the catheter method and Finepress method for blood pressure measurements. Use the sample statistics you calculated in the questions above to answer the following questions. Note, assume that the population of differences is normal. So first of all, they're writing this because our sample size for those blood pressure readings is only 15. We're supposed to have a sample size greater than 30, or we need that the population we are drawing from is normal. So that's why they've written that note here. So first, number 10, determine the critical value T sub C that corresponds to the 95% level of confidence. So first of all, what we need is the level of confidence, 95%, and we also need the degrees of freedom. Remember that degrees of freedom is sample size minus 1. So in this case, that's a sample size of 15 minus 1 is 14. So go back to the table that we had in a previous lesson. Find the critical value that matches with degrees of freedom 14 and 95% level of confidence. What you will find from that table is T sub C is 2.15. So then number 11, determine the margin of error for a 95% confidence interval for the population mean of the paired differences. So here, our margin of error is E equal to T sub C times our sample standard deviation divided by the square root of sample size. So this will be 2.15 times, I'm going to take my standard deviation for the sample differences, that was 8.573. And then divide by the square root of my sample size, so square root of 15. So I'm just going to type 2.15 times 8.573 divided by the square root of 15, and then rounding to 3 decimal places, approximately 4.759. Number 12, compute a 95% confidence interval for the population mean of the paired differences. So I will take my sample mean minus the margin of error, and then also the sample mean plus the margin of error. So our sample mean from earlier was negative 2.933. So negative 2.933 minus the margin of error, 4.759, and then negative 2.933 plus the margin of error. So negative 2.933 minus 4.759, that gives me negative 7.692. And then if I take negative 2.933 and I add 4.759, I get positive 1.826. And then number 13 says, review the confidence interval in question 12. Based on the confidence interval, can you conclude that there is a difference between the Finipress and catheter measurements? So if there was a difference, think about what that would mean against an earlier question where we asked, what if there was no difference? Earlier we said there was no difference if the difference between those two methods gave us 0. What we can notice from our confidence interval in number 12, 0 is in the confidence interval. How do I know that? Because the lower number in the confidence interval is negative and the upper number is positive. 0 is between those two. So since 0 is in the confidence interval, this is indicating that there is no difference.